All right, hello everybody, and welcome to this Friday afternoon lecture on numerical integration and why we care in chemistry. So again, let me just briefly mention that whenever there is a question, please use the chat so we can talk about that immediately. Okay, so what is numerical integration? So what's the main purpose of it? And the idea is you have proper integrals, so with integration limits, of some function which you'd like to evaluate. And now the catch is that sometimes you don't have an analytical expression of the function. I'd say in practice, more often than not, you don't have this. And numerical integration is one way of working around that particular problem by assuming that you can just evaluate the function at a certain set of points and then sum things up. So basically, this replaces the integral by a weighted sum. And the main 2 degrees of freedom that you have is at which points you evaluate the function and how you weigh these individual points. So the different approaches we're going to discuss, they largely differ in these 2 degrees of freedom. And for an honest comparison, of course, you'd like things to be comparable, so the total number of points you're evaluating shall be the same for our comparison. Another reason why you might want to do that is if your evaluation is expensive. So for example, if you want to calculate pKa values, then each individual point in computational chemistry calculations typically is going to keep your average cluster busy for about a week, maybe 2. So you don't want to have so many points of this. Therefore, you want to find a way to deal with few points only. So let's look at the strategies, the main problem in this. And now you can argue, well, you just take some points, pick some points, and weigh them, maybe take the average or something, and this way you get an integral. Well, yes, but also no, because the question is, which points are relevant? If you look at the left function, and if you take a regular interval of points everywhere, then you largely, about 2/3 of your data points are completely useless, because the function is 0 everywhere. So it's a constant value over here, and then you have this narrow peak thing, and then it's 0 again. And particularly in chemistry, this appears often, because this is how an electronic density looks like. Electron density around some nucleus is going to have largely this shape. And if you want to integrate densities, then that's the common problem. Now, you can say, all right, then I just use more points, I cover the whole domain, and then life's easy. Yes, but then you're going to have too many of those. So imagine this boring function on the right side, and if you know how it looks like, 1 point is enough. But if you don't, then just few points should suffice. So it's always the balance between just having boatloads of points and then make the problem solve itself, or by being too sparingly using additional data points to support the method. And the basic concept of having all those many points and then summing things up, that's exactly what an integral does. So if you maybe remember the derivation of the integral definition as a limit expression of the Riemann sum, where you have these finite domains where you just add up individual bars, that's exactly the kind of concept behind numerical integration. So what kind of objects do we have in chemistry where we need numerical integration? Because there is nothing else, or hardly anything else. So here are a few examples. So one of the most promising or prominent problems is electron densities. So for example, if you look over here, then Kato's cusp theorem tells you that the electron density decay, spherically averaged around some nucleus, depends only on the nuclear charge of that nucleus. So you have something which is highly peaked and gets peaked even worse the higher the nuclear charge is. And that's hard to integrate any of this, in particular since many practically relevant properties that you, for example, would use in experimental setups rely on integration over that density. So, for example, the dipole moment that you can use for interaction with a molecule or selecting them or rotating them, the dipole moment is the integral in space of the density times the vector. So density is rho here. And the ionic force, so in the Born-Oppenheimer approximation, the force acting on every nucleus, again, is an integral in space of the electron density. And the quadrupole moment, which you, for example, use in an ion trap, you again have the integral over the density. So the one problem is, in this case, how to integrate things reliably. And the other problem is how to do this with as few points as possible, because getting the density at one point in space can be expensive. So another area where this comes into play, for example, in experimental setups, is that typically the integral of a peak is related to, say, absorption properties. And that's typically a very narrow function. I mean, it's called peak for a reason. So the integral thereof is something you would like to determine with as few data points as possible to support that one peak, because you only have so many. Okay, so let's talk about the basic concept, because pretty much all numerical integration methods follow the same procedure. They just differ in technical details how they do some things. So for the sake of the game of this lecture, we're gonna again assume that we have a bounded function. So this means no infinite points in between. It shall be smooth, so differentiable, and it shall be defined everywhere over some integration interval that you're interested in. So this is basically what people mean if they say for sufficiently well-behaved f. This then renders this integral amenable to a straightforward approximation by a finite sum. If you have all these nice and shiny guarantees over here, then nearly all these integration methods do the following. They approximate the function f with polynomials. Why is that? Because you can integrate polynomials arbitrarily accurately. I mean, it's just a pure polynomial. I can do an analytical evaluation of the integral, so that's sufficiently easy. Now, you usually don't use Taylor expansion for that, because the Taylor expansion is designed to work for one point, but we actually care about the whole domain of A to B, and that's why we need this whole integral, and that's why we need to separate points or to use points spread out over the whole integral. And there are some numerical details as to why you want polynomials. I'm not going to go into that. Now, the problem is that a function may not be a polynomial. And what you do in these cases is you try to make it more like a polynomial by dividing it into regions. So you say, I use a quadratic approximation because quadratic functions are nice, I like them, and they are typically accurate enough. So I would like to just approximate things with a quadratic function. Now, if your function, for example, has a turning point, then that's not a quadratic function that you can use for approximation. And rather than going to higher order, so to cubic functions, quartic functions, what you do is you take your whole domain, so the area, the interval A to B, and you split it into parts. And then you say, I do my quadratic approximation for each of those regions. And generally speaking, that will work, because if your domain is small enough, then you are in the quadratic region of the function. So at that point, think of the discussion of optimization algorithms where we had exactly the same thing, that for a small domain around any point, you can make things quadratic. So this concept of subdividing your total interval for which you're interested, subdividing this into a partition, so a complete set of subintervals, that's called composite integration. And that's usually the winning strategy. I'll show some numeric results for that later on. Now, if you choose a certain set of polynomials as approximant, then you just say, over the whole domain, I would like to approximate my function f with, say, a cubic function, cubic polynomial. Now, you need to get the coefficients thereof. And that's exactly what these weights are. So if you do the derivation, you can take your cubic function, you can integrate it analytically, keeping all the coefficients as variables, and then later on calculate what these alpha I should be if you had the individual function values at certain points. So this means if you decide on the scheme, so which polynomials to use, and on where to evaluate this, so evenly spaced, different spacing, different regions, then this determines the weights completely. So the nice thing is that all your degrees of freedom in this thing is the choice of what kind of polynomials would I like to use and where would I like to evaluate things. And then the alpha I, they plot out by just solving the system of linear equations. And people have done that for very many different schemes and procedures. And usually there is no one way that works best. There are different ways that work in a different amount of cases, but typically you're going to have to look into your specific integration problem to pick a suitable one. And I will try to convince you of that. Okay, so let's first talk about the points, because I think that's the more intuitive thing you can adjust. And now you can say, why would I care? I just take evenly spaced points over my space and then everything is nice. If you look at this, so here we have the function x times e to the minus x squared. This is the function you see in each of the plots down here. Now, if you evaluate the points and interpolate linearly between those, then depending on how you go about it, you get different kind of accuracy. So if your interpolation would be perfect, then the shaded area that you see here, this triangle, would be the same as the integral of that function, which is obviously isn't. Now, you can either use the same number of points, so 5 points, and be clever about where you put them. So for example, this point over here went away, and rather this interval from 0 to 2.5 has been subdivided twice. So this is similar to the concept of importance scaling. You focus on one part of the functional domain, such that your integral in the end now is a better approximate, because now the shaded area is more close to the integral of the actual function. The other way of doing things is saying, is no problem, I just take more points. That's what you see here. So you add more points, and then of course the approximation becomes more accurate. I mean, technically you're approaching the limit of the Riemann sum more closely, but you also add more points over here, and they cost. I mean, they might not cost you on evaluating this function, but if f is expensive, then adding more points in this area does not improve your integration whatsoever, because they all have the same value. And so the main catch is you don't want to just brute force add more points to it, because practically in many cases you can't afford that. So the rule of thumb is adding more points makes things more accurate, but at what cost? So your mileage varies with the different methods that you might apply. And the other approach is to be clever about the coverage of the total integration domain. like here in the middle panel, where we put points in those regions. That's typically a very advanced problem, because if you look at a function, it's hard to tell whether there is one domain which is more relevant than others. And if you think carefully about that, then you realize that this must have something to do with the gradient of the function, because the gradient is nothing, is 0 over here, but is non-zero over here. So very likely one could use the gradient in order to decide where to integrate. We're going to see that later. All right, so, but this is not the only source of error. So this is just about the points, right? So where do I evaluate my function? The other degree of freedom was which kind of polynomials do I use in order to do the whole interpolation in the end. Because in this picture, what you see is we have linear functions between the points, and this is garbage. Because maybe if we had something like quadratic functions between, that would be a better approximant of this integration function. So choosing those individual polynomials is a little bit of a challenge, and people have tried very many different things. And usually the best concept is that you choose some low order polynomials and then a dense spacing. That's spacing of points. That's what typically works out best. That's why I mentioned initially the composite integration schemes, where you follow those into numerical integration rules just on smaller domains. Now, since you do a polynomial approximation, this means a polynomial of nth order does not include anything, any character of the function that has a higher order than that. But the next highest order, so the n+1 derivative, that gives you an error bound. And that's a nice thing about the numerical integration schemes, that you can, given sufficiently well-behaved integrants, you can give proper bounds on their integral value. And the bound typically depends on the next highest order derivative that you have in your data. So here what we have is a linear interpolant between these individual points. If it were quadratic, then it would be the third order derivative that dominates the error. Here it's the second order derivative, because we see here there's this turning point which we don't capture the maximum, because we just go linearly between the points. Now, the nice thing is that for almost all integration schemes, smaller intervals reduce the error. But how quickly they do, that depends on the integration scheme. So there are some polynomials which have better convergence properties than others. And we're gonna see those individual examples separately. But for each of these examples, for each of those integration schemes, we will encounter a certain limit that the computer apparently can't surpass. And I would like to explain why this is. So a certain limit in accuracy. And I've heard Anders has mentioned this a little bit. I would like to go into a bit more detail on how and why this problem exists. This problem is called machine precision, or machine epsilon, epsilon being the smallest non-zero number that a computer can describe properly. And the reason for that is that a computer, based on its hardware design, has a finite precision with which calculations are done, typically. And that's something that's common in all programming languages. That's why I have an example in Python and in C for exactly the same thing. And that's purely a hardware design. So you can think of it as, if you were to do long division manually, then you're going to stop at some particular accuracy, and you're going to say that's fine, that's good enough for me. And you have to do this in order to finish your long division at some point. So that's precisely what the computer is doing. It calculates with a finite precision and basically a finite number of significant digits. And for practical purposes, you can just memorize that the number of significant digits is roughly 15. So it largely does not matter what's the absolute value of the number you care about. You can trust the first 15 digits, ballpark. And strange thing, I mean, it's kind of obvious if you think about it, but it's a strange thing we have to keep in mind, is the math in the computer and hardware and silicon is done in base 2. So 0.1 is inexact. It's in binary, 0.1 is the periodic representation, meaning that the computers are going to truncate. So famously, if you do any kind of equation involving 0.1 in your Python interpreter or Google Colab notebook, you're going to realize that there's a small deviation from the actual number. This only applies to floating point calculations, because anything else, so integer calculations are exact, or at least you can have them exact. But for floating point representations, the problem is you're going to stop adding digits at some point. Typically, the most relevant sources of error are summation and multiplication. So here I have brought you one example. If I have one variable called a and assign 1 to it, now I can have another variable b, and I can say take whatever is in a and add 10 to the minus 10. So now a lives on the order of 1, and this lives on the order of 10 to the minus 10, so they're separated by 10 significant digits. And that's something, if I now print the difference between 1 and b, I would expect to get minus 10 to the 10, and that's something I get. So this is perfectly fine. Here you see this is minus 1 times 10 to the 10. Then there is some noise over here, which comes from the finite representation of floating point numbers. But you see here, the concept worked just fine. So I basically have 1 minus 1 plus 10 to the minus 10. So that's exactly what we have here. Now, what if I make the second number smaller? So it's the same code between the two, but now this is 10 to the minus 20. So they are separated by 20 significant digits, which is more than the 15 I mentioned, meaning that the result is 0, because this 10 to the minus 20 just vanishes in the representation of 1. It's too small to be representable with the given significant digits, meaning that in this equation a is essentially unchanged, and that's the reason why the answer is 0. And you have the same thing if you do this in C, to clarify on the fact that it's a hardware issue, not a programming language issue. I'm going to have this with anything you can program with, unless you take special precautions. I'm going to mention that. Here you have the same logic in C, and note that the first number has exactly the same kind of noisy digits than this expression had, because it's the same thing that happens in the background between two programming languages. So keep in mind, whenever you sum, in this case, a large number and a small number together, then things can go wrong very quickly. I'm going to show another example for that in a bit. So that's one of the reasons why for algorithms, for example, for summation, you'd like to use a library, because libraries usually at least try to avoid some of these problems, and you don't want to implement the special summation algorithms for each and every addition you might make in Python. Now, usually the summation algorithms are slower than plain addition, so that's the reason why Python doesn't do it on its own. There are typical workarounds for this kind of problem. So the first one is, you can just say, all right, I have my floating point number, but integers are exact. So you can represent your floating point as 2 integers forming a rational number. And then you decide on the precision how many significant digits you need by making those rational numbers just larger. And then your fraction becomes more accurate. And in fact, calculating the best rational number approximation is actually quite easy, but it's tedious. And that's why there are special libraries for that, that can do this for you automatically, transparently, so you don't have to worry about that. The other thing is you can group summations. So for example, if you integrate or if you add lots of tiny numbers, and then a few large ones, a good strategy typically is to sort them and add them from small numbers to big numbers. Now, of course, this costs this additional sorting, but is numerically more stable. That's often the reason why algorithms are written in a certain way, such that this sorting is inherently obeyed. And the other thing, what's typically done is group summations. So if you always do pairwise additions between numbers, then this allows you to reduce the average numerical error you get without sorting. So it's more like a heuristic argument. In Python, in plain and simple Python, there's one of these things implemented. So if you have a long list of small numbers and you would like to integrate it to add it up a bit more reliable than NumPy can do for you, then you could use from the math module, which is part of regular Python, you could use fsum. That is uses a better algorithm for that. But if you really care, then you'd like to use the dedicated libraries for that. And this being Python, there's always a library for it. This is called mpmath. And mpmath as a library can do arbitrary precision, really arbitrary precision, as long as you provide sufficient memory and patience to wait for the result. So for practical purposes, mpmath is not noticeably smaller or slower. But if you do some heavy calculations, it's going to be substantially slower. So in many cases, if you care about precision, then mpmath is going to solve it. I would like to show you how exactly, and to illustrate why this becomes a problem or can become a problem very quickly. If you look at this slide, then please look at this equation over here first. So we have a series. We calculate a series, a sequence that looks exactly like this. So the nth element of the sequence shall be defined as 10 over 3 times the previous one, minus the one two before, so the second to last. So it's a bit like the Fibonacci sequence you use the last two entries. And if you initialize this with a0 being 1, and a1 being 1/3, after that you just apply this recursion formula, then you can show that the nth element of this should be 1 over 3 to the n. So effectively this converges to 0. Now the problem is that this is hard for the computer to model. More precisely, for this to converge, you need a certain condition in the variables involved that is really hard to satisfy if you just have a few significant digits. So this is what you see here. This is the relative error. So whatever Python tells you divided by the true value it has. And this is the series iteration. I mean, this is not far. So regular Python breaks down after less than 20 iterations. So where the first two being those numbers. So it's about 15 iterations after which Python is not able to describe this accurately. So your error increases. That's the blue line hidden behind the red line over here. So this over here is the relative error, and this is awful. So at 40 iterations, you're 23 orders of magnitude away from where you want to be. Now, this is just the result of this consecutive usage of finite precision data points. And with mpmath, I'll explain the code in a bit. With mpmath, you can set how many significant digits you'd like to carry over. And what you see here is if we choose the 15 digits, the ones I mentioned as ballpark number before, if we choose the 15 digits, then you get the same behavior as with a native data type, which is a double, which can roughly hold 15 significant digits. Now with mpmath, we can first make our precision worse. So we can see what's with 5 digits, with 10 digits, and that's the orange dashed and the green dashed line over here. So you see they all can diverge eventually, and they all diverge before the 15 digits one does. But also with mpmath, we can say, how about more digits? If we set it to 50, then you see this thing diverges later. I mean, it still diverges because you still have finite precision. You can just talk about the point at which it does. And that's exactly what this line over here is showing. So in those cases, the different precision that you set just defers the time at which the calculation doesn't pan out anymore. But that's fine, because for practical purposes, you can now tune things. And to be perfectly honest, if you add more digits, things become slower. Again, the no free lunch theorem strikes. So let me just briefly explain how you would program this in Python and how you would do that in NP-math. I mean, there's no sense complaining about it without explaining how to do it better. So let's first look at this implementation over here. So we have a list which contains the first two elements of the sequence, so 1 and 1/3. And now we continue with this by iterating over this, always appending the last entry times 10 divided by 3 minus the second to last entry. And then we return the list. So that's nice and easy. So how would you do the same thing with NP-math? With NP-math, you import it like so, and the common abbreviation for this is MP, because you're going to type this a lot. So first, you can set the precision. So DPS is digits precision, meaning in base 10, how many significant digits. And whenever you use a number, you have to initialize it like this. So you say MP for the library, dot MPF, meaning float. And then you give the string representation of what you like this to be. Because obviously, if you just plug in a float here, then you have the same precision as you would have in Python, because there's no more information. But this way, the library knows that this has to be an exact one, exact to this many digits. And that's why the 1/3 over here is more precise, because now this one gets approximated to 50 digits, or whatever you specify as precision, rather than to this limited precision that Python typically works with. And now we do the same thing. So every number you just replace by this wrapper. So mp.mpf, and then you replace it by the number, and then you can do all regular math operations the same way as you did before. And if you do that, so for example here we just use whatever's in the list, then you get this kind of accuracy. So, and then for the exact one, we have the same concept where we just always multiply with 1/3 in order to get the next entry of the sequence. So the main takeaway message here is, with this kind of library, you can get arbitrary precision math in Python. And the core concept of this library is exactly the rational number representation. Okay, so with this finite precision argument in mind, let's have a look at numerical integration. So if you look at the plot bottom left first, so here we have two functions. They look pretty much similar. So we have the function f of x, the blue one, and then we have g of x, the orange one. And they are defined on the same domain, so from 0 to 1. And they are both analytical. I can write them down, as you can see here. And they look fairly similar in feature. I mean, if you were to shift the orange one a little bit to the right, then it would have a substantial overlap. So these two functions shall be our test cases to see how well these different approaches work. The key message is they look pretty similar, but their behavior for numerical integration is much different. So again, just as we did this with the optimization algorithms, I would like to explain the different strategies first. So the one family, it's always a families of algorithms. One family is again Newton, but Newton codes. So the idea is you use equidistant points. This is typically helpful if you can choose the points at which you would like to evaluate your function beforehand. So here you can, if you have some QM calculation, you often can't. Now, the second class of family is Gauss integration, or Gaussian quadrature. And typically, it's non-equidistant points, but still predefined. So they are just irregularly spaced over the interval, and that typically has advantages in precision. The other family is trapezoidal rule. If you just have arbitrary points, it's the closest to the Riemann sum concept. And the last one, which is something you're also going to explore in the exercises, is the Monte Carlo integration, where you just look at random points. And I'll explain why this is useful in a bit. Now, if you want to do molecules, then you would like to have a very special integration grid that is more suited to the purpose. And we're going to discuss this. This grid is called a Becker-Lebedev grid, and it's designed to be suited for electron densities. So in the molecular context, you're likely going to use this. For plane functions, you're likely going to use one of those. Okay, so let's have a look at the simplest one, Newton codes. So the basic idea is you take equidistant points in your integration interval, and you use a certain set of polynomials. They're called Lagrange polynomials. And this is implemented in SciPy integrate as the function Newton codes. And this is particularly helpful if you have your bread and butter regular problem that you don't really care about. So something well-behaved, smooth, nothing fancy, small integration domains. So let's say something that looks like a safe bet. That's where they are pretty useful. Now, if you look at the plots at the right, I would like to explain them a little bit because they're going to appear for each and every integration scheme. On the x-axis, we have the number of points. That's how many data points we are evaluating our function, at how many points. So effectively, we would expect that as we add more points, things become more accurate. And on the y-axis, we have the integration error, because all those functions I can integrate analytically. And if I do, then I know what's their true integral. Now I can compare that to what we have in here. And the first one over here is for this function f of x, and this is for g of x. So those were these two functions that we have here in the plot. Now the interesting thing is they behave differently. And for many of the plots, so where it makes sense, we have the two cases. So the plane, that's just applying the rule on the whole domain, so 0 to 1. And the composite approach, where we subdivide our interval into smaller intervals and apply the rule to the integration rule to each and every interval separately in sum bosa. And this is totally fair on the x-axis. So in the composite case, this is the true number of function evaluations that we compare. And this red line over here, this red line is the numerical precision. So that's the best you can expect for anything that involves numerics, because afterwards we run out of significant digits. Okay, so what we see here is that for the one function, this is very nice. So it converges continuously. At some point, it diverges. So for the plane one, and the reason for that is numerical instability. But if we rather decide to use smaller and smaller integration intervals, so in our composite rule, then what we get is a continuous improvement, although initially we converge a little bit slower than with a straight application of the integration rule. But if you look at this function over here, so here our plane integration scheme starts off pretty nicely, but doesn't really get better, and then diverges. And even with a composite scheme, it's more well behaved, it's improving by adding more points, but significantly slower. even though the two functions look pretty much similar. Okay, so how would you do that in plain and simple Python? So this is one example over here. So you can load SciPy integrate. I like to give it these 3-letter shortcuts. And the point is you first write a function, the function that you would like to integrate. So your integrand should take a value and then return whatever belongs to that function you'd like to integrate. And then what you can do is you can use the Newton codes function call in SciPy. And this function call takes exactly one argument, which is the order of the Lagrange polynomials you'd like to include. So how many points you're going to add. And what you get is two things. You get the weights of your equidistantly spaced points, and you get an associated error estimate. What you don't get are the points. So the points you need to get separately, and that's what you can do with the NumPy linspace call, which gives you equally spaced points, namely order plus 1 many between the lower bound and the upper bound. So this then is all the integration points at which you would like to evaluate your function. So that's exactly what you do here. So you call function over all those points. And if you remember from Anders' lecture, this xs is a vector, and this in NumPy is a valid operation of the whole vector. So you get this element-wise. So basically, the function applied on each value within xs. And this you multiply with the weights you got from SciPy. You can sum this up, and now you need to normalize this by the spacing of these points, because the weights don't include that, since they can't know your spacing. And the result of that then is your integral. So if our function is x squared, this way from 0 to 1 to order 2, we get 1/3, which is the correct integral. Okay. So this makes sense, but it's not as great in terms of integration performance. And that's why in practice, the Gauss quadrature often makes more sense. So this is the same concept, the same data for the Gauss quadrature. So again, on the x-axis, we have our integration points, and it's the same scale. And for the y-axis, we have the integration error. Now what we see here is that within the steps, we quickly reach our total limit. So the machine precision limit that we can expect. And the same goes for the other function. So G is still easier than F, because F reaches machine precision later, but the Gaussian quadrature works better. And the main difference is the points at which the function gets evaluated, and they are based on the Legendre polynomials. So that's where this typically comes into play. There's one catch. The Gauss quadrature only makes sense if your endpoints of the functions exist. So you can use Newton codes if at the boundaries, the lower bound A and the upper bound B of your integral, the function is not defined. Then you can use so-called open Newton codes. That works. In this case, the Gaussian quadrature requires that the endpoints exist. Now, the nice thing is that SciPy makes it easier for you to use this thing. So it's implemented again in SciPy integrate, and the function fixed quad for quadrature. And again, we have our function call xs, and you can just directly call SciPy, so no additional functions required. You just tell SciPy fixed quad, you specify which function you'd like to integrate, so the name of this. You say from where to where, how many points, and then you get your answer. So again, we get our 1/3. So for all practical purposes, if you can choose the integration points, then the Gaussian quadrature very likely is what you want. If you can't choose your points, and they don't happen to be the ones that you need for the Gaussian quadrature, or for Newton codes, then the next best thing is the trapezoidal rule. And it's nice conceptually because it's easy. You just make lines between whatever support point you have, and then you integrate this piecewise. The catch is it converges awfully slow. So again, we have our points here on the x-axis, and we have our integration error on the y-axis, and you see we are nowhere near machine epsilon. It's going to converge eventually. It's going to take very, very long time to get there. So this is basically a piecewise linear approximation. And it's integrated, it's implemented in this function traps, trapezoidal. I don't know what they do with these 5 characters that they save, or 6 characters. In any case, this is the function that can do it. And this trapezoidal integration rule works better than the others in exactly one special case, if you have a periodic function. And this makes sense because think of this, of the linear interpolation. If you have a quadratic function, then you're missing out on some part of your integral, but you miss out on the same thing on either end. Let me maybe draw this. So if you have something like a periodic function that you would like to integrate, and now you say I evaluate it here and I evaluate here, then you're missing out on this part of the peak. But now you're going to make the same error on the other side again. And that's why the trapezoidal rule is typically more accurate if you use a periodic function with the same amount of points. It's also easily implemented with one nasty catch. Whoever implemented this prefers their order and arguments for the y's to be first, not the x values. So unlike all other SciPy integrate functions, this is reversed. So again, you have your function that calculates x squared, and then you say, I get my x values, in this case equally spaced from 0 to 1, 40 points. Calculate the function value, and then you calculate this with the trapezoidal rule, whatever belongs to this integral. And now, if you remember that for all the other methods, this was pretty much 1/3, you see the precision is awful for the fact that you had to do 40 points. So for anything non-periodic, if you can avoid it, trapezoidal rule typically isn't what you want. Okay. So what we have is now the major families, but there is one very graphical, very visual thing that I would like to show you, because it's very helpful if you care about higher dimensions. So all of these methods we've seen here, they work pretty nicely in 1D. And if you add some extra effort, they might work in 2D. If you want to get this to work in higher dimensions, you're going to have a problem. Mostly because the number of points you need to add explodes very quickly, and the numerical stability of things degrades. So for anything which is a higher dimensional problem, you usually either have domain-specific integration techniques, like for our 3D case with the electron density, we have this Becker-Lebedev grid. I'm going to talk about that later. But for your general case, like arbitrary function in higher dimensions, have to be a little bit creative. An interesting concept that works beautifully is called Monte Carlo. So the basic idea is you collect random points, truly random points. And if you look at the 2 figures on the right, then what you see is that here we have one function that we'd like to integrate. It's again our x squared case. We have our domain from 0 to 1. So now what we can do is we can say this is our whole area from 0 to 1, from 0 to 1 on both axes. And now we generate random points. I mean, if I generate 2 uniformly random numbers, so one number between 0 and 1, I have my x coordinate. Another number between 0 and 1, I have my y coordinate, so this gives 1 point. Now I can calculate the function at this point, And I can compare whether I'm above, so not part of the integral, or whether I am below, so part of the integral. And if I do this sufficiently often, then what I get is a ratio between the number of cases where I am below the function and the cases where I'm not. So this means you get the ratio between this part of all that area and this part of all that area. The trick is, if you choose the whole area over which you generate those random numbers to be as small as possible, but larger than your integral domain alone, and easy to calculate, then that's fine. Because I know that this one is unit distance 1, this here is a unit distance 1, so this whole thing has the actual area of unit, so 1. Which means that if I have this ratio of, say, 40%, then this would mean that my approximation of this integral here means 40% of the points are here, 60% are here, so 40% of the whole area is the integral of my function. Of course, in 1D this makes no sense, because we have seen that we can integrate this much better with fewer points, but the 2D case or the 1D case is a little bit easier to see than the higher dimensional case where you actually use it. So this is pretty much helpful if 3 conditions are satisfied, or to put it in a different way, unless you have a better idea, this is the fallback. So the one case where this makes sense is if your problem is high dimensional, and 3 counts as high in this context. Mostly because there are a few reliable other integration schemes that you could use. This also helps if you have something which is highly irregular, because the random nature of this helps you to also get the points in the important regions. So of course, if you have something which is very narrow support, so it's only non-zero in a small domain, then you have just a limited chance of actually hitting it, that it's still going to work, unlike, for example, equally spaced points, which either get you this domain or they don't. So at least you have a probabilistic argument in this case that you're going to find something eventually. And the other requirement should be that the individual point is cheap. Why is that? Because you're going to need boatloads of data points. If you again look at our x squared quadratic function, so if I want to integrate this from 0 to 1 with abysmal accuracy, I need 10,000 data points. I mean, this should be 1/3, and this is far away from 1/3. I would just like to explain how to do that in Python, because this is not something you have in SciPy Integrate, but it's actually fairly easy to implement. So it's a standard programming problem to write this on your own. So we again have our function that just squares things. And in this code, I just assume that we just have this domain from 0 to 1 and from 0 to 1 over here. If we do that, then first we need random numbers. And you can get random numbers from NumPy using np.random.uniform. And this uniform is going to give you uniformly distributed numbers, meaning every number between 0 and 1 is equally likely. And you have to then rescale this by the whole domain, so such that you get this in the right area. If this wasn't 0 and this wasn't 1, then you need this additional case to just make this evenly distributed over your integration interval. And the y values are just these, the x value squared. Now you need your random y values to compare against. And this again, in our case, we assume that this interval here is 0 to 1. That's why we can just use this uniform number of points. And the order over here is just the number of points where we're asking NumPy to give us randomly. So now we can ask NumPy again, in how many cases is this compare smaller than the y-s value that we have calculated. So what's the ratio of the points below? So how many points are below the curve as compared to the whole number of points we did? So NumPy where gives us a list of indices. A list of indices where a certain condition is satisfied. So compare is one vector, ys is the other. This is an element-wise comparison because in NumPy, unless specified otherwise, everything is element-wise. So this gives a long list of either true or false. And NumPy where gives us all the truths. With 0, we select the first axis. There is only one, but that's how NumPy works. And we specify that we like to know how many there are because we don't really care about where they are. They're random after all. So afterwards, below contains the number of cases, the number of points which are below that, the random points which are below the function value. So below, over order being the total number of points we have, is this ratio. And if we multiply this with our total domain, so the area over here, then this is the total function value. In our case, this is just 1. So it's the ratio of below, so the number of points below the function over the whole area that gives us this. And you can imagine this works in any kind of dimension, as long as you get those random points. So this was 1D. Let me show you this with 2D. And I would like to explain this a little bit in terms of convergence. So as you can see in the right panel only, this is to estimate the area of a square, which is one way of calculating pi. So the traditional thing you show people in Monte Carlo integration. Now, if I can calculate the area of this, which is the success rate in my Monte Carlo to have something close enough to the origin, such that unit distance is small, then I have here 10,000 points. I think this is 100,000 points. This is 10,000. This is, I believe, 100. So the main point being that with just few data points, you have a hard time recognizing what's the thing you're integrating. And this converges very, very slowly. So in practice, you need very many points, but the nice thing is you can always watch the integral. So you just add more points, and then you see at some point the integral value doesn't change anymore. So you now, all right, this is now converged. And one thing that's maybe not obvious in that context, random numbers can be expensive. And there is no true randomness for a computer anyway, at least unless you take special precautions. But these random numbers, they're going to take some time to get, in particular on older hardware. And this basically means that this Monte Carlo integration is, again, a method of last resort. So the same way as in the integration scheme and the optimization scheme, we have this grid search as the method of last resort. Here we have Monte Carlo, just because the convergence with number of points is so bad. Okay, so with this in mind, what are practical problems that you have with any integration methods, any of these? So, of course, the first obvious enemy to reliable numerical integration are functions that have just local support. So they're non-zero in a very narrow area of your domain. And think of it as line shape functions, which are inherently narrow. So that's pretty tough to actually localize the domain where they are non-zero and then integrate all those non-zero domains reliably. In that case, the effort is quite substantial. That's why there are cases where you do adaptive schemes, which I don't want to discuss here because that's a long lecture on its own, where you try heuristics in order to figure out which regions you would like to integrate. So if you think of this kind of function that we've seen in the beginning, this data point is useless. This data point is also useless. If we would know that beforehand and use these 2 points in order to improve the capture of this peak, then of course our integral in the end would be more accurate. The other problem might be high local curvature. So if you think of this step function, the blue function in the background, then it has an infinite curvature right here, or here, depending on how you look at it. And this is awful to interpolate from polynomials. So if I have all these points in these regions and I interpolate things with polynomials, then this is what you see here. The individual functions, if you add more orders, they never really are of the same shape. You get these errors, this oscillations over here. And this means that even if you add more points, integrating this function is not going to work if you use one polynomial for the whole domain. And that's one of the reasons why composite integration schemes, so where you use piecewise polynomials, are much more reliable, because then you can choose, for example, this point over here, 0, to be one of those points separating intervals, and suddenly your integration scheme is much more accurate. So that's one of the reasons why high curvatures are a tough problem. The other problem is the function should be representable in those polynomials, and that's the only reason why these 2 functions f and g that we have looked at, why one of them is harder to integrate than the others, because the polynomial expansion of one is significantly harder or requires higher order than the other, and that's the only reason why they 2 differ. Their curvature is roughly the same. So in that case, the choice of polynomials was crucial to the performance, as we've seen that the Gaussian quadrature is much more reliable than the Newton-Cotes quadrature. If you just want to do higher dimensions, then the main reason why you can't really do that is because your number of grid points increases substantially. If you have grid spacing, then this is the nth power of the number of grid points in every dimension, and that's expensive. So that's why for high dimensions, you typically don't do regular grids, you do this probabilistic Monte Carlo approach. There's another problem with polynomials, and that's something that applies to polynomials in general. It's called Runge's phenomenon, and the idea is polynomials work very nicely in the domain they care about, but they don't work far away from that. So this, for example, here is the same interpolation, the same we had before. Again, it's the step size function and the step function and the different polynomials. You see that the third order does anything after the actual interval above which it has been defined, and the higher orders, they explode at the boundaries. And this thing is called Runge's phenomenon. So basically, polynomials become very unreliable at the boundaries of an interval. You can maybe see this little bit here with this red spike at the boundary. So the interpolum is quite nice over all that region, but towards the end it gets unreliable again. And this means that if you have something which is not very well described by low order polynomials, then the likelihood that your integrand gives you unreliable numbers increases with increasing order. And that's the reason why you don't want to go to higher order polynomials and just one quadrature, so one integration, but why you, in practice, you always want composite integration schemes, which then do the integration just on a small interval. All right, this was all 1D. So that's, for example, relevant if you do line shapes or if you want to integrate model functions that you have. Let's look at molecules. So this is what we can do for molecules. On the right side, you see the electron density in the bond axis for some N2 dimer at 1 angstrom distance. And this is the actual electron density. Note that this is the electron density in the bond axis. That's why you don't have these broad peaks that have a high non-zero value in between. That would be if you were to integrate over the whole plane perpendicular to the bond axis. But if you look at this, as I promised before, these are very narrow peaks. So they tick, electron densities tick several boxes on the list of things that are bad for numerical integration. They are local. There's only electron density where you have a molecule. They decay exponentially, meaning they have a very high, steep slope, high gradient, which makes the error estimate worse. They are inherently 3D, and they are unsuited for regular grids. You can easily see that because if I have a regular grid that is, let me change this. If I have a regular grid that gives me one data point here, and with one data point here, I've missed that peak completely. So that's not really helpful. And even if I have very narrow data points, whether I get a value over here or whether I get this value is going to change my integral a lot because the peaks are narrow, but it's just random relative positioning. So whether the position at which I actually inquire the function is how this is relative to the atomic positions. This actually has a funny name. It's called the egg boxing effect. So bottom line, regular grids are pretty bad for electron density integration or molecules in general. And what people quickly have realized is that for any reliable numbers, you'd like to have special integration grids. And one approach that is, say, fairly popular in this context is to put spheres around every atom. Because this Gaussian decay that you see in the figure, this exponential decay, sorry, it's not Gaussian, it's exponential. This exponential decay that you see here is the same for, is conceptually similar for all nuclei. That's behind the Katos-Kasp theorem, which tells us that it's an exponential decay, which just depends on the nuclear charge. So the other thing is it's roughly circularly symmetric. So the hard part in where actual chemistry happens is not the overall shape of the density. This you can get with very crude approximations to quantum mechanics, but is the small deviations from that shape that actually makes chemistry, that makes bonds. And so to a very good degree, some spherical sampling around atomic positions is pretty accurate. So what you do is you have sphere surfaces around every atom, and now you sample the surface of the sphere in a systematic fashion. And Lebedev has figured out how to do that. It's based on harmonic spherical functions, spherical harmonics. And he has a way, or just derived a way, how to get quasi-random relevant points on a spherical surface. Now you take these spheres and you make them very small. So you have something very narrow around the nucleus. And then you add more spheres, which just have a larger and larger radius. And these radii you make exponentially spaced. So initially they're very, very close together, and far out they decrease in density because your sphere becomes larger. It's more about the average effect that you care about. So these two approaches together, so one, how to sample a sphere, and two, how to get them exponentially decaying, they together are called the Becker-Lebedev grid. And they come in different quality settings. Basically, the Lebedev thing, the Becker qualities are less important, but how densely you are sampling your sphere, that's the relevant question. Now, to implement this is awful. And the reason is not because Lebedev equations are so hard and not because the Becker equations are so hard, but the reason is that a molecule typically has more than just one set of atoms. So there's more atoms than just one, meaning that these spheres, they overlap, and you have to account for that. So the weight discounting on how the spheres for this atom take into account the other atoms, that's part of the Becker scheme, and that's the hard thing to implement. So the nice thing is, this being Python, there's always a library for that. And what I hope that is one thing that you take away from this course is at least the names of the relevant libraries that are going to solve your problem. So I'd like to show you two such packages. So the one is QuadPy, which you can get with pip install QuadPy. If you run this in Google Colab, then you need to put an exclamation mark in front of this. And QuadPy, for quadrature in Python, gives you many integration schemes for very likely more 3D objects than you ever have cared for. So if you want to integrate a three-dimensional triangle or a pyramid, then QuadPy got you covered. But it also has, and is one of the most convenient to use integration packages I know, it also has very reliable implementation of this Becker-Lebedev grid. Sorry, of the Lebedev grid, not of the Becker part. So this is a mathematical thing. I think the author behind QuadPy aims at implementing any numerical integration scheme that they can get their hands on. And they do a pretty remarkable job on it. So the idea is you first need to get a scheme. So what do you want to integrate? So you import QuadPy, and then you tell QuadPy, this is about a sphere, and from all those 50 methods you have on how to integrate a sphere, I would like to choose one of the Lebedev ones, namely the one of ordinal number 19. So Lebedev grids exist in special magic numbers, so to say, and 19 is one of them. And then, once you have this, you can call scheme.integrate. You give it a function that you would like to integrate, and you give a point around which this is to be centered, and you give a radius. And what you get is the integral of a spherical surface. So this exists for very many different objects, spheres, balls, whatever. Keep in mind that Lebedev integrates the surface, not the volume. And if you want to take this to the next level and look at molecular grids, then one package can do that. It's called PySCF. And the for PySCF methods, this aims at implementing QM codes or whatever you need for a QM code in mostly Python. So it's not all Python, but it's mostly Python. And we're going to use this in the remainder of the course a little bit. You can get it on Google Colab. Again, put this exclamation mark in front if you run it on Google Colab. Otherwise, this works on your regular machine. And in the context of density functional theory, these Becker-Lebedev grids are commonly used, or at least different flavors thereof are required. And this is the reason why it's in that DFT submodule of PySCF. So you first build a molecule because this contains the atomic positions. And then you call that function and you get a grid. And then this grid contains coordinates and weights. During the exercises, you will use this here on the right. The exercise will contain more of a sample code, so showing you how to build a molecule and how to use this. That's the core of that exercise, such that you get yourself a little bit more familiar with PySCF. So whenever you're looking for a molecular grid, even if you don't do the calculation in PySCF, that's again one of the most convenient methods I know in order to get this Becker-Lebedev integration grid points with the associated weights that account for the position of other atoms. So there was a question And the question reads whether this, what we had on the previous slide, this density profile was calculated with B3-lib, so one of the hybrid functionals used in the computational part. No, it isn't. This is Hartree-Fock 631G, so the Pocal basis set. It doesn't really matter, because the interesting thing, maybe as a side note, the interesting thing for electron densities is that across functionals, so be it Hartree-Fock, be it B3-lib, PBE, you name it, the densities are actually very, very similar. What differs is the energy, so where the accuracy comes into play. And the reason for this being that the electron densities are dominated by the fact that you have a nucleus here, and that this forms the singularity in the electron density distribution. And they are much less affected by chemistry, so how the electrons interact with each other and how the bonds are forming. So that's why if you compare the electron densities, they're almost always going to be the same. You can imagine that you can get a pretty good approximation to this if you just place plenty of free atoms right next to each other, because they're all going to look like this. So non-interacting atoms and interacting atoms have very, very similar density distributions. So B3-lib would be typically the more reliable choice, because typically gives better energies than the Hartree-Fock approach. But on that slide, if I were to plot both, you wouldn't be able to distinguish them. All right, so with this, we have seen how to do numerical integration in SciPy and in NumPy, so both the Newton codes case or the Gaussian quadrature. We have the code examples on the slides. We'll also look at QuadPy, which maybe is a nice thing whenever you remember that you have a more complex integration problem. You might want to remember QuadPy. And whenever you want to do molecular calculations or molecular integration, you might want to remember PySCF. So to summarize, we have seen the different methods. We have seen when they work. So Newton codes, if you want to have equally spaced points, Gaussian, if you can care about non-equally spaced points. The trapezoidal rule, if you care about a periodic function. Monte Carlo, if it's high dimensional and you don't have anything better. So whenever you find something in QuadPy, that's the better option. But if you don't, then Monte Carlo it is. And we have looked at molecular integration models, the Becker-Lebedev grid. We have discussed that in particular high dimensions are a problem. Again, the local support, so it's the same, basically the same concept as an optimization lecture, and that high curvature is typically related to, or high gradients are typically related to a higher integration error, depending on what order of polynomial you look at. And we have checked in Python how you can do integration for both functions and molecular geometries. So with this, today's lecture would be over unless you have any questions in the chat. I don't see any. So if that's not the case, so I wish you all a very good weekend, and I'll put up the slides and the video shortly. Thank you very much.